In this video, in the next series, we're going to talk about orbitals as they apply to molecules. And so we've seen the atomic orbitals, the s, the p, the d, but how do we use those to make molecules? Well, first we kind of have to talk about the type of molecules. This only applies to covalent. And as such, there's a lot of rules about how many electrons you have to share. Remember, a covalent bond is about sharing electrons between atoms. And so our first step in this is Lewis structures. A Lewis structure is an easy way to draw a molecule to show you the bonding. To do this, we have to figure out the number of valence electrons. Remember, on an atom, let's say carbon, we have our 1s, our 2s, our 2p's, 1, 2, 3, 4, 5, 6. Carbon's element number 6, it's going to have 6 total electrons. Well, it's only the outside edge electrons that really can interact with other atoms. When you bring two objects together, the outer edge is what meets first, and those are the ones that start repelling or interacting. It is the valence electrons, the outside edge electrons, that we care about. And our valence electrons is whatever our highest occupied shell is. So our shell is the 1 or the 2 or the 3 in front. It's the n value for your quantum numbers. In this case, for carbon, the valence orbitals are the 2s and the 2p. It's the whole shell. And so if we look at carbon, it has 1, 2, 3, 4 valence electrons. And the fact that it has 6 total is irrelevant. It is only the valence that we care about. And for our covalent molecules, we're really only going to care about the s and the p. In theory, if you had an element that was in the n equals 3, you could have 3 Ds, or if your element, was in the n equals 4, you'd have some 3 Ds around, but these are all transition metals. We don't care about the 3 Ds, we care about the S and the Ps for finding our valence. What do we do with those valence electrons, however? Lewis structures treats the s and p like they're identical. As we'll see in later videos of hybrid orbitals, this is because we mix the system up and they're not really different anymore. We'll get to that more in time. What we think of is that for any element, there are 4 valence orbitals, the s and the 3 p's. We just draw them equivalently, but we spread them out. We say, hey, there's a top, bottom, left, and right. Those correspond to the 4 regions, the 4 orbitals. And if you have an electron, you can put them in one of those regions. And you would spread them out before pairing them in an orbital. Much like we see here with the 2 p's, we spread them out in equivalent orbitals before we pair them. So for carbon, with 4 valence electrons, you would spread its 4 electrons out in the 4 regions. But if we have nitrogen, well, nitrogen has 1 more electron. So nitrogen would have 1 more electron. It would have 5 valence electrons. For nitrogen, you'd put 1, 2, 3, 4. And your 5th, well, there's no open region, so now you have to pair. It doesn't matter which is paired. It could be the top, it could be the bottom, it could be the left, it could be the right. By convention, we often throw it on top. But it doesn't matter. They're all equivalent. So you can place that 5th electron in any of the 4 regions. Well, this trend kind of continues. Oxygen, 1 more element over, has 1 more electron. So it has 6. 1, 2, 3, 4. Start pairing for 5. And start pairing for 6. Fluorine is 7 valence electrons. And so you would place your 4 and then pair 3 more. And neon has 8 valence electrons. You place your 4, and then you'll end up pairing all of them. We can also go backwards to boron. It has 3 valence electrons. Hydrogen comes up often. It has 1. There's an easy way to tell without trying to draw, though, the columns. So our S block and our P block are the ones we're watching for valence. To know the number of valence electrons, just count how many from the left. 1, 2, 3, 4, 5, 6, 7, and 8. You'll notice that the third column has boron, and boron has 3 valence electrons. The fourth column has carbon, and carbon has 4 valence electrons. So even if we had something like sulfur, well, sulfur's underneath oxygen. That column has 6 valence electrons, and so we would expect sulfur to pair 2 of its regions and have 2 with only a single electron in it, just like oxygen. If we tried to figure that out from the drawings, well, sulfur's element 16, 1s, 2s, 2p, 3s, 3p, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. What we'd see for sulfur is its valence is the 3s and 3p, and it has 2, 4, 5, 6 valence electrons. So those columns, because they correspond to your configuration, will let us very quickly identify the valence electrons on each element. So what do we do with these valence electrons? Well, the whole idea of a covalent bond is to say I have hydrogen over here with its electron. I have another hydrogen over here with its electron, is that they can overlap. The opposite proton will be attracted to the opposite electron as well as its own, and so they pull towards the middle. Those nuclei pull towards the center to get nearer those electrons. Well, one electron came from each, and they formed a bond. If I have a hydrogen and its 1 electron, and I have a hydrogen and its 1 electron, I can simply bring them close. Those electrons are now overlapping their region. Pull back and say, hey, here was each in its own orbital, and as I overlap them, I can overlap those orbitals to get those electrons to both be in the other atom's orbital. This is how we form a bond. We overlap the orbitals. Often what we'll do for a quicker drawing, hydrogen dot, line between them to show that they are now sharing with each other. Simplified drawing is just a dash. We put a dash between elements to show a bond. That bond is those 2 electrons. There are 2 electrons sitting in there. Well, only unpaired electrons can overlap. If you're already paired, you can't have more electrons in your orbital. But an unpaired electron, well, that's a different story. So if I have a carbon, and I'm going to attach hydrogens to it, I bring one up and it can overlap with one of carbon's unpaired electrons. I can grab another hydrogen, do it a second time, grab another hydrogen, do it a third, grab another hydrogen, do it a fourth. This will be CH4. This is methane. Why is methane CH4, not CH3 or CH5? Because carbon has 4 unpaired electrons that it can use to bond. It doesn't have 3 unpaired and it doesn't have 5 unpaired. It has 4, which means it can make 4 bonds. If we did this with nitrogen, NH3, ammonia, Well, we would put down nitrogen first. Always put your atoms down with their electrons first. Do not bond until after you have set up the atoms and the electrons. Now you can move your hydrogens all over, but you generally are going to want them somewhere where they're near an unpaired electron. So we put it on the sides near the unpaired electrons. We pair any unpaired. Make it look a little bit nicer. And we have ammonia. Why is nitrogen with hydrogens only NH3? Because nitrogen only had 3 unpaired electrons. It could only make 3 bonds. We'll see similar for water and for HF. Water's oxygen starts with 6, our hydrogens with 1. Pair the unpaired and you get oxygen with 2 hydrogens because it only had 2 unpaired electrons. Fluorine has 7 total, so only one of them is unpaired. You just get HF. And finally, neon. Well, hydrogen can't bond anything on neon. There's no unpaired electrons. Our noble gases are unreactive because they have no unpaired electrons to react with. This is the basic idea of a Lewis structure. It lets us investigate why our molecules have the number of bonds they have based on the valence electrons of those atoms. We'll continue with examples in another video.